this subpart of the lecture number 10 of Physics 401A, we will try to find the Lagrangian for a system of particles which are no longer free. For free single particle, we showed that the Lagrangian should have a form of half mv square. Okay, and for a system of such non-interacting free particles, the resulting Lagrangian will simply be the sum of that half mivi squares. Okay. Now, if we have a system of particles which are no longer free, okay, which are no longer free, but interact with themselves, okay, so that means it's an intra-system interaction. This constitutes an isolated system of particles. Okay, very frequently in Landau's books you can see the word closed system. So that was the ancient terminology. Nowadays we say this is an isolated system. So a closed system basically can exchange energy, okay, thermodynamically speaking, but it cannot exchange mass, okay, with the exterior. But an isolated system can neither exchange energy nor exchange mass. Okay. So such an isolated system of particles which are mutually interacting with each other, they are our center of interest for now. The question is how to insert the effect of interaction. Okay, the effect of interaction in the Lagrangian. Okay, so now if we assume that this effect of interaction will come in an uncoupled way to the free particle Lagrangian, then we can simply say that if we add this interactive part, which we can write as L star interaction, okay, that can simply be, if added to L free particle total, would give us the total system's Lagrangian. Okay, now you just have to remember that LF total is the sum of the n particle systems Lagrangian when the n particles are free, okay, or non-interacting. Now L star is not a Lagrangian by itself, but it's just the net effect of this interaction which should be added in the total Lagrangian of the system. Okay. Now let us call the second term as minus of a scalar function u. Okay. And we further assume that this interaction term should be a function of the instantaneous positions of all the particles. That means that should be a function of R1, R2 up to Rn. Because we want to consider only those type of interactions which depend on the instantaneous configuration of the system. That is our, pre-designed motivation. Okay. Now U changes instantaneously as the configuration changes, right? That is very easy to understand from this form. That simply says that whenever the configuration changes, okay, the signal or the information about the interaction, about the new interaction or the new configuration is basically propagating with infinite speed. That means it is immediate that the system is receiving the information about the change of the configuration. Okay, and that's why we say that this is an ideal assumption. So basically, as you know, that no information can propagate with a velocity greater than the light speed at vacuum. So basically that's why the assumption which we do here is basically idealistic, but for the time being we will assume that. Okay. Now if we apply Euler-Lagrange equation in the whole, in this system's Lagrangian form, that is T minus U, where T is nothing but the summation over half mi ri dot square minus U, u is a function of r1 to up to rn, then simply we can write, just if we are concentrating on the ith particle, okay, then the corresponding Euler-Lagrange equation will simply give us ddt of del L system. System means, I mean, L system is the Lagrangian of the whole system. Then the Euler-Lagrange equation will be ddt of del L del Ri dot vectorially minus del L del Ri vectorially, okay, is equal to 0. And if you do that, you see that del L system del Ri vectorially is nothing but the minus of nabla I. That means this is the gradient with respect to the space coordinates or the position coordinates of the ith particle over the scalar u, and ddt of del L system del Ri dot is nothing but mi Ri double dot. That means just the acceleration of the ith particle. So if you now try to understand that the Euler-Lagrange equation finally says that these two are equal, and that finally gives you mi Ri double dot is equal to minus gradient I of u. So basically this is something which causes the acceleration of the ith particle, right? Okay. And of course, when the acceleration is multiplied to mi, that is exactly equal to the minus of the ith gradient of the scalar function u. And this can be thought to be the force acting on the ith particle. And this is nothing but Newton's law of motion. So a priori there is no surprise, because beforehand when we derive the functional form of L as t minus v or t minus u for a conservative mechanical system, then already we started from Newton's second law and we reached there. Now we started from t minus u or t minus v and we have reached Newton's second law of motion. That is just the other way around. Okay. Now as we know that this is the correct form according to our previous knowledge, this is the correct form of Newton's second law of motion. Basically that is a way to cross check that t minus u is equal to L, which we assumed for a system of mutually interacting particles, okay, basically is a valid assumption, or the form is a legitimate or a reasonable form. Okay. So that's why we somehow, just by guessing, and it's a trial by trial method, basically we put that and we showed that this gives us something which we already know in its correct form, that is the Newton's second law. Okay. And that's why we know we somehow can cross check that t minus u, that means if we have a number of mutually interacting particles, then the Lagrangian will simply be the summation over the kinetic energies of all the particles minus a representative potential energy of the whole system that depends on the position coordinates, instantaneous position or instantaneous configuration of all the particles. Okay. Now note that u is defined only to within an additive constant. That is also true from your knowledge of Newtonian mechanics as well, that potential energy is always defined with respect to an arbitrary base reference, right? And that additive constant has no effect on the equation of motion. Okay. Now we are trying to find the Lagrangian of a system with external interaction. So till now we said that we have found the Lagrangian of a system of particles which are interacting within themselves. But how should I write the Lagrangian of a system which is moving under the action of external agency or external entity? So instead of isolated systems, we now discuss the form of Lagrangian for a system A, which is interacting with external agent, that is another system B. Okay. So let's say A is already containing n particles. But now we are not talking about the interactions of the n particles within A. I am talking about that the interaction of A with another system of particles B, let's say. Okay. Now since A plus B makes an isolated system, if we now think that the universe is constituted only by A and B, then A plus B makes an isolated system. Okay. So now we can think that for the greater, the universe has two parts, A and B, and they will behave like as the constituent particles of the universe now, A and B. So using that, we can finally write, using the previous section's discussion, Lagrangian of a system of particles with mutual interactions. We can simply write the total Lagrangian will be Ta, that means the kinetic energy of system A, which is a function of Qa and Qa dot. Basically here I am just writing the representative generalized coordinate and velocities that can be of multi dimensions. Okay, it is just for brevity I am writing just Qa and Qa dot. They can be Qa1, Qa2 like this, and Qa1 dot, Qa2 dot like this. Okay, plus Tb, which is the kinetic energy of B, okay, minus U, which is a function of Qa and Qb. Okay, now you can simply ask me that in general that when we talk about kinetic energy, the velocity arises. Yes, it's the usual case, the velocity arises. And if you remember, we said that for a the kinetic energy, basically when it is written in terms of the generalized coordinates or generalized velocities, basically, then there is no guarantee that you simply have this you simply have terms with the quadratic terms of generalized velocities. There can be cross terms which should come, which are nothing but the functions of the coordinates themselves. Okay. Now, including that, we can finally say that kinetic energy in general can always be thought as a function of both the coordinates and the velocities, generalized coordinates and the velocities. Okay, the same thing here for A and B. Okay, now U, according to our definition, it should only depend on Qa and Qb. The potential should not preferably be depending on Qa dot and Qb dot. If that depends, that's another story. Okay, now our goal is to extract La. Okay, the Lagrangian for a system A. Okay, in the field of an external entity B. We are no longer interested in B. Okay, so we have the whole thing and we have to extract the La so that B is considered as giving an external agent. Okay, and how to do that? So we can do that by solving explicitly. So you have the total Lagrangian. Now you can solve for QB and for QB dot. Okay, basically you can solve QB and QB dot in function of time just by using the Euler-Lagrange equations with respect to the QB and QB dots. That means you have to use the Euler-Lagrange equation of del L dot del L QB minus ddt of del L del QB dot is equal to 0. Okay, that you can do. If you do that, then you will have the equations of motion by which you can solve for QB. And if you know QB in function of t, okay, as a function of t, then by doing QB dot, you will have QB dot as a function of t. Then you solve everything for system B. So the whole system B can now be written in terms of time explicitly. Okay, and that also can be done without affecting Qa and Qa dot, right? So once you do that, then just using L total and the Euler-Lagrange equations, once you do that, okay, then we replace QB and QB dot by their time dependencies respectively. Okay, we will write everything of QB and QB dot in terms of time. Then what happens, that L dot can be written as TA QA QA dot plus TB will be simply TB of time, and TB of time can again be written as a DDT of a pure function of time. So this will then will be a DFDT, where f is a function of time, so it will work as a gauge, okay, like a a term with of symmetry transformation of Lagrangian. So basically and the last term minus u qa qb will now be simply u of qa and t. So qb's role will now be replaced by t, okay. So basically you see that if I call this ta qa qa dot minus u qa and t to be la, then L tot will be equal to La plus dfdt. Now La and L tot, one is differing from the other just by the total time derivative of f, which is a function of t. So they will give the same equations of motion. So basically the thing is that we can finally claim that we can have a Lagrangian, okay, something like the Lagrangian t minus u, which is a function of qa dot and t, okay. So it can be claimed as a function of as a Lagrangian of the system only the system system A only, okay, because it involves only the coordinates and the velocities of the system A and time, okay, plus dfdt, okay. So basically you can say that this La, which can now be thought as the Lagrangian of the system A, is nothing but the L tot, but everything written in all but L tot, but every B system variable, that means QB and QB dots, are written in terms of that time, okay. If you can write that, then only you can say that L dot and La, they are just differing by dfdt, so both of them are giving the same equations of motion. So La is not different from L dot. This La, which is nothing but then Ta qa and qa dot minus u qa and t, basically then can be written or can be represented as a Lagrangian of a system which is moving under the interaction of an external effect, okay. Now basically the external effect here is designed by the virtue of the system B, okay. And the only difference from the normal t minus u is that here the u is containing t, and that t is coming as the reminiscent, okay, as the reminiscence of the qb and qb, actually qb, okay, which is now written in terms of t, okay. So you see that what will be, so the question is that what will be the equations of motion corresponding to La? If you know L tot, and if you can write everything in L tot in terms of qa dot and t, that means you eliminate all the qb and qb dots in L tot, then you are already done. You don't have to find La every time, because L tot written in terms of qa dot and t is giving the same equations of motion as La, okay. That's the message. So the Lagrangian of a system interacting with external entity can still be an usual t minus u type, where you can now be an explicit function of time as well, okay. So finally, if we try to write the total Lagrangian of a system of particles, both interacting within themselves and also moves under the external field, then this will simply be given as the kinetic energy, total kinetic energy, okay, which is the function of all the velocity vectors. Now that velocity vectors, when they are written in terms of the generalized coordinates and generalized variables, then you will see that both the generalized coordinates and generalized velocities appear, basically, although here you just are are vector dots. Here you have both qi and qi dot, and this is another function actually, t prime, minus u internal, that means the intra-system interaction, which is a function of r1 dot 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 up to rn, and that will simply be written now in case of generalized variables, minus u like internal, okay, of qi's, minus u external. Okay, of course this also be another, this may be another function actually, this is another function, let's say u prime, okay. And finally the external thing, which will be the function of ri dot 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 up to rn and t, and the same thing here, so it will be minus u external prime. Of course there is another prime because this is not necessarily the same functional form, and this will be a function of qi's and t, okay. So you see that finally we write the Lagrangian of a system of particles which are interacting within themselves and which are also moving under the action or in the field of external agency or external agent or external entity, okay. So using these things, now you can solve several problems, several many body problems, okay, in classical mechanics using Lagrangian formulation. Thank you very much.